I hope you had a good dinner yesterday evening. I was not there, so I cannot tell. So this is the fourth day, right? The fourth day, one more day to go. Now what I want to do today is with you, basically we want to continue with this outline of the lecture, right? And we now get a little bit more closer into a research example where we talk about something called broadcast control. Before we do that, I want to step a little bit through what we talked about yesterday in the lecture, just to recap. So, and if you kind of like take out the 2-3 most important take-home messages from yesterday, then perhaps you remember that we talked about survival. We made this example, are humans actually CPS, right? And we said, okay, there's a certain, let's say, algorithm or functionality inside of you, and that's actually inside of all living organisms that are moving around. This functionality is essentially ensuring survival, or in the old days it ensured survival. And it's basically a feedback loop. That's all it is. In order for this feedback loop to run, to perform according to your survival, one aspect of it, not all aspects, but one aspect of it is this capability of providing a real-time response according to the dynamics that are going on outside. Okay, good. So taking that into account, right, we moved into the domain of networks and mobile networks. We talked about the evolution of telecommunication systems. This is like, by and large, over the last 200 years, what was going on. And we came to the conclusion that communication systems kind of like evolve in waves, where the first wave was basically characterized by communication between humans, pure communication between humans. Also talked about the fact that this is associated still to survival, or a strategic advantage. There's nothing surprising going on here. It's all the same principles. We just transform it into, let's say, what we would call a technical domain. But the basic underlying needs, the basic underlying, you could say, advantages that it gives you, that's all still there. Okay, good. And this was dominating kind of like the evolution of communication systems for 150 years, roughly, 150, 170 years. And then when computers were coming up, kind of like people figured out, oh, there's a second type of application that we can actually run. This is a much more powerful application than pure human-to-human communication. And this is the underlying principle here is taking out the man in the middle, in all kinds of arbitrage processes. Right? And we made that example of stock markets. The same applies to you booking flights, or you doing any other type of, let's say, document modification. Now the key thing here is that there's still a human on one side of the communication, but typically the other side of the communication is already given by a computer. That's where you store your information, where you access, you retrieve the information, and you modify the information. Okay. And overall, this is then the evolution of the internet, essentially. This was what was driving the internet from a business perspective. And this has been much, much, much more powerful. And you can already say that to a certain extent, into this second generation of telecommunication systems with this client-server architecture, here you already start to map parts of reality into an infrastructure. The fact that prices of stocks today are stored on a computer is a cyber representation of something actually physical going on. In the case of stocks, the interesting thing is the physical thing has been scrapped by now. But when you're booking a flight, that's still there. So there's a representation of the flight. You can book into those resources. You can modify the representation of the flight in order to such that they give you access to the flight. So we're already in that area where in here we're starting to bring in the cyber domain, just like in cyber physical systems in general, or as it's also running inside of your brain. Your brain is all about just representing what's going on in reality. Okay, so we're already heading in that direction, but we're not fully there. And the thing that distinguishes that we're not fully there is the real-time aspect. What we map into client-server applications today, or also over the last 20, 30 years, this is all super slow. This is mostly super slow stuff, unless we want to really invest a lot of money. And then we're in the business of high-frequency trading in New York on the New York Stock Exchange. And with one or two people yesterday after the talk, we already started to discuss into that direction. So you certainly know the real estate in New York around the server locations of the New York Stock Exchange. These real estate places are extremely expensive. And the only reason why they're expensive is that everyone wants to be as close as possible to where that representation of reality is stored. Likewise, there are companies running cloud computing centers on the ocean, on the bottom of the ocean, in the middle between London and New York. Why are they doing that? They want to do arbitrage business between London and New York. And so from a latency perspective, the best location to be with your compute is in the middle. So they sink that stuff 3,000, 4,000, 5,000 meters to the bottom of the sea. Okay, so unless you're very wealthy, or you're the military, where you also don't need to care about money. In this kind of like in what we have been seeing so far, basically we already map reality into digital infrastructures, but we don't have this real-time notion yet. It's hard to realize this real-time notion for really fast dynamics, unless, as I said, you have a lot of money. Okay, and now this third wave of telecommunication systems that's now coming up, that's all going to be about more or less digitalizing the rest of reality, and then it's also a lot about real-time reactions, feedback. The key thing is feedback. Is the feedback coming in time? Okay, so if you look at contemporary network architectures, this is how every network virtually in the world today, and let's say in the digitalized parts of the world is running. So you have all your handhelds, you have your mobile networks, you have the internet backbone, and you have your cloud centers. Right? So if you now start to think about how do we, right? So how in this infrastructure, what are the challenges if we want to introduce now lower latencies, if we want to generate feedback in time? Well, then the one thing is the compute capabilities that are around are either here on the one end, or they're here exactly on the other side of the internet architecture. And that incurs, relatively speaking, high latencies. And in the panel discussion yesterday, we made this example, right? So is edge computing really necessary if we have 5G? And I was saying you cannot beat physics. So if you need, let's say, a round trip time on your feedback loop of 100 milliseconds, or of 50 milliseconds, that incurs a certain maximum physical distance where your point of computation needs to be located, unless we have a couple of advances in physics first. And that means we need to somehow beat speed of light in the transmission of information. Okay, good. So the one thing is the latency, and the other thing is that virtually any endpoint today is connected wirelessly. Yes, there's still wires around, and they're significant, but by the huge majority of these connections, of the stuff that is connecting to this infrastructure, to the cloud centers, is all run over wireless connections. And the big desire, let's say it like that, of the cellular networking industry is to tap also into these real-time feedback loops with wireless communications. And here we run into the problem of reliability. And then we talked a little bit about that, right? We said, okay, so in order to get our hands around here the latency aspect, what we will do is we're going to introduce these compute nodes being much closer to the endpoints, right? So we're going to deploy now compute nodes somewhere along your internet routes. And that is very elegant because on the one hand side, we get physically much closer. So just from a pure fundamental perspective, the latencies that you can generate from this point of computation are much, much better, whatever is in the middle. The other advantage, and we didn't talk about that so much, is that this thing here in the middle, that's the world of the so-called internet protocol. And the internet protocol is great. There's nothing wrong with that fundamentally. The one thing is it hasn't been built for what we want to do here. So essentially, there were two competing concepts for how to run the internet by the beginning of the 90s. The one was this internet protocol, kind of like advanced and proposed by Silicon Valley-based, software-based companies. And really, I don't think, or maybe it's a little bit exaggerated to always ponder these stereotypes. But IP, if you look at IP is like a protocol where you just say, okay, make it run. Don't engineer it, just make it run. It's a hack. It's fundamentally a hack. The competing concept to IP was something called ATM. And ATM was coming from the telecommunications industry. At that point in time, that industry was much stronger, was much more dominating, had much more business than what was going on in Silicon Valley at that time. These guys were engineers. They had a protocol around where they said, wherever you are on the world, I can give you a guaranteed latency from that point to any other point with this thing called ATM. Now, the world didn't evolve towards ATM. Engineering is kind of like out of the window. We're all living with a hack here in the middle. It's a great hack. Nothing wrong with the hack. Okay. So by bringing the compute closer to these endpoints, here, this beast in the middle, we don't need to touch that. And here we're talking about millions of really large internet routers, and you don't, and they're all hardwired. They're all legacy to Cisco, and you don't want to substitute. You don't want to substitute that infrastructure. So by bringing the compute closer here to the endpoints, we don't need to deal with that mess in any way, and that will be a nightmare. Okay, so that's what's going to happen. And the main driver for this edge computing is, on the one hand, these feedback loops in the context of control, in the context of CPS, in the context of what we're talking about, what this summer school is about. But just as a side note, there's an equally important or even more important application where we have so-called humans in the loop, where we have applications that are going to be guiding you. They're going to giving you perceptual feedback in one way or the other. Okay, and this is an extremely powerful application because it always taps essentially into what we as humans are doing, not you as humans, what all of us as humans are doing, and we can essentially kind of like start again to put in business models where we save time. And one significant example here was, think about tasks that you have never been performing, but right now you need to perform them, and you're kind of like trained in that skill, but you're not exactly trained on that task. So what you then do is you kind of like just download a corresponding task guidance application to your augmented reality glasses, and for example, a surgeon who's then usually used to, let's say, treating knees, who specializes in knees, could perhaps also start to just treat feet, and with a much better precision, with a much better outcome for the patient. Likewise, your workers in a shop floor, in a manufacturing site, can be brought up to speed, can be assigned much more flexibly if you have such systems. And that's where we're going to make a lot of money, but only if we have corresponding feedback loops that are bringing in this perceptual feedback in time. Now, when it's about task guidance, these loop times that we're interested in, they're typically in the range of 200 to 500 milliseconds. So when they're beyond 500 milliseconds, kind of like the humans operating these tasks, they kind of like get a little bit irritated. What am I supposed to do next? And then they do a next task, and this is recognized, but the feedback is not coming instantly, so they think, oh, I'm heading in the right direction, right? And they do the next task, and this is just hard to operate. But as long as your latencies are somewhere below 300, 400, 500 milliseconds, you're good. Now the thing is, you might say, 500 milliseconds, right? That's even enough to kind of like get the data to the cloud and back. And in principle, that's right. The one thing that is wrong here is, in order to generate this perceptual feedback, you need a lot of compute. You typically burn 200-300 milliseconds for the compute. And that eats into your latency for just shoveling the data back and forth. The other thing is the sensory input in the case of humans in the loop is very, very often video, a video stream. And you all know, right? So video streams are kind of tend to eat up a lot of bandwidth. So that's exactly not what you want to stream in the millions up to the cloud centers. So that's another argument why not to shuttle that further down the road. But this thing here is again adhering to this principle that whatever is going on here in reality, there's a representation of that here at the edge node. And from that representation, we then generate some feedback. Okay, and in the case of CPS, that's the case anyway. Right? That's just a good old, let's say, closed loop, the closed loop control thing, where you have sensor information, you run your computational algorithm, you give some actuation feedback. That's much more straightforward to see that, of course, you're operating on a representation of reality. And I think most of you with a control background also know if that representation of reality is not up to date, right? If that is kind of like outdated, then whatever you do here on the feedback is typically causing more harm than it's doing good. Okay, so these are the two major application classes. And this is what we're going to see over the next 10 years driving here these edge nodes. There's a third class where we're purely interested in analytics of videos and analytics in general of data. So it's only going upwards. There's not much feedback coming down. That's a third application class that is driving the proliferation of edge computing. Okay, good. But we want to deal here with these feedback loops. And so the first problem now is how to get the latencies right in general. Right? And the way to do is to bring the compute nodes closer. And that solves two problems. IP is gone, and we're much, much closer. Right? The second problem, though, and that's how we then concluded yesterday, is essentially that wireless communications is not necessarily reliable. We talked a little bit about why that is the case. So we have this electromagnetic wave that we're emitting from an antenna. This wave is then kind of like traveling out into all different directions. That's also not a big problem yet, but when all these waves kind of like start to reflect and bounce off of objects, right? So typically at a receive antenna, you're receiving a large amount of signals from all different directions. And that is bad because we get then this constructive and destructive superposition of these electromagnetic waves at the antenna. And this is a purely random process. It's nearly impossible to predict that over a horizon longer than, let's say, 1 or 2 milliseconds. It's just not doable because you have to model too much of the physical environment, so to say. Okay, and that leads then to these wild swings of your received signal. And this is therefore now the second issue that we somehow have to address. And that's how we stopped yesterday. Good. Now I want to know from you what do we do? Right? So how do we tackle that? What's the way to go?
You can put in several antennas, multi-antennas on separate.
1 second. Let's stay first with what the first sentence was. We can put in cellular towers.
Several antennas.
Yeah.
Multi-antenna. So you get
Aha.
physical distance between antennas.
You mean on the transmit side?
On the receiving side, only there.
Okay, so on one of these two sides, I put in multiple antennas. That's what you're saying?
Yeah.
Yeah. And then? So then I have 3 of them. And they're now emitting, let's say, all the same signal, and these signals all still bounce off and recombine.
No, on the receiving side, I mean.
Yeah, okay.
So you sort of, one antenna has more signal than the other.
Yeah.
At certain time.
Yes, exactly. How do we call that? There's an underlying principle here. Yeah, it is a type of redundancy, exactly. There's a more, let's say, when it's about risk in general, right? Also in financial markets, right? So whenever it's about risk, what do we do?
Redundancies?
Yeah, we don't call it, you never read in the Wall Street Journal redundancy, right? Did you ever? I don't know. I didn't. I don't read it that often though. Yeah? But yeah. So hedging, yeah. Exactly. So this is what we need is diversity. We need to kind of like put our eggs into multiple baskets. And here the key observation is, so you have a wireless resource, and the wireless resource, so what I mean by wireless resource is now a connection from one point to another point. And now the quality of this wireless connection kind of like evolves over time. It evolves over frequency, or it kind of like has a state in frequency. And in that sense also has a state in space. So there are three fundamental dimensions of wireless resources: space, frequency, and time. And the funny thing is, or the really good thing, is that these fading processes, they're from a certain separation in these three frequencies, in these three dimensions these processes become independent. Meaning what happens at this point, at the start point here on the wireless communication channel between two antennas, is statistically independent to what happens like 200 milliseconds later. Now, if I play that in time, that's of course not a good idea. If I try to harness that in time, because what I don't want is I don't want to wait, right, in my CPS applications, in my closed loop applications. So that's not a good way to go. But if I look at the same thing in the frequency grid, so this is just the same snapshot that we saw previously. We're just not resolving only the time dimension here. We're also resolving here into the frequency dimension. So what I can do is I can kind of like start to transmit in frequency on 2, 3, 4 frequencies at the same point in time. And if the separation in the frequency domain is large enough, what I'm sending is actually becoming, or the receiving power at those corresponding frequencies is becoming statistically independent. And that's a good thing, right? Because now I'm mathematically in a very nice regime, right? Where I can kind of like arbitrarily decrease any error probability that is happening. Okay, and that's exactly the same thing in space. So I can put up multiple antennas, and if these antennas are spaced apart by a sufficient amount, then the transmission between the received signal between any transmitting antenna and any of the receiving antennas is also becoming statistically independent. Okay, and that's in wireless communications. That's known as diversity. We're harnessing diversity. And fundamentally, what is happening in 5G, apart from further advantages in how you parameterize the system and you know how you deal with a spectrum in general and how you deal with the backbone, what they put in for these feedback loops, for these what is called ultra-reliable low-latency communication systems. Maybe some of you have heard the term URLLC, as a terrible acronym. What they put in essentially is just a lot of diversity. That's the way to go. That's the only thing that we can actually do. Okay, good. So we put in diversity, and now we want to kind of like switch a little bit gears here, and we want to dive into a concrete example. Yes, 1 second. Let me find what I want to show you, and then we're here in the game. Full screen. Thanks a lot. Good. Okay, you had a question.
Yeah, so you had the picture of the fading.
Yeah.
And the diversity is the solution to this problem.
Yeah.
What do these graphs look like with the diversity?
Okay, that figure that I was showing, that I just put away. So that's just a snapshot of the receive power between a single transmit antenna and a single receive antenna. If you put in diversity, the first question is, how would you visualize that, right? Because
the previous graph, how does the previous graph look after you've introduced?
You mean this one?
Yeah.
Yeah. Okay. So, okay, then essentially what happened, okay, so let's say the following. So let's say you have a single transmit antenna, you have 2 receive antennas. Okay? Or let's say you transmit on 2 different frequencies. And then what you do at the receiver is what we call maximum ratio combining. So we just combine the both signals, and we kind of like weigh them according to the signal strengths that we measure up front. And then what essentially happens is that these swings get much, much, much smaller. So the variance of the received signal reduces, and kind of like it all kind of like centers around the average that you would be expecting for that distance. So that's what's happening. Sure. Okay, good. So I want to advance here to my other slide set, and I hope this is going to let me do that. Here we go. And okay, good. All right. So this is work now together with people from control theory here from KTH. So Dirk van Doren is a PhD student of mine. This is something Dirk was presenting in December at CDC, where we're now looking at closed loop control, where we run the closed loop control over an edge node. We have wireless connections. And we come up with an extremely simple system design. And we put in a little bit the mathematics also of the system design, and then study how effective it is in order to tackle the problems that we just saw. Okay? So what we do is we anticipate this edge computing scenario where the latency is towards the cloud, IP that is all gone. We mainly deal with the question what to do with the wireless communication channel. And if we do that in a particular way, in a simple way, what is then the quantitative impact actually on the control system? That's the basic intention of this work. There's the full paper on my webpage. Dirk is perhaps also running the full paper on his webpage. You perhaps also have access to IEEE databases, so if you are interested in more details. Okay, good. And this is the basic setup. So we have a plant, and we want to control that plant over wireless link, and we have a particular compute resource. Now, in wireless communications, apart from the fundamental stochastic uncertainty of the channel itself, for majority of systems that are out there, there's a second problem that you need to overcome. And the second problem is that typically when you're in a certain environment where there's not only one transmitter, one receiver, but there are multiple transmitters, multiple receivers, you somehow have to agree on an order in which they are transmitting. This is called medium access control in the networking lingo. Now, the stuff that all of you are carrying in your pockets and that all of you have at home, and that is perhaps also somewhere here in the room, but I'm not finding it right now. So Wi-Fi, what is actually Wi-Fi doing? How is that organizing the medium access control? Does anyone know that?
It divides the band in channels.
That's true. That's how it's separating different access points from each other.
CSMA.
CSMA. How do we explain CSMA without getting into technical details?
It detects the presence of energy in the
You're
channel.
already in the technical details. What is CSMA?
Just listening if there's something going on there.
Yeah. And who's also applying that? By coincidence?
Humans.
Humans. We do that all the time, right? Carrier sends multiple access. So listen before talk. You're not, I don't know about you, but I'm not always listening before talk. But these situations are characterized, are quite striking, or they have certain, let's say, dynamics going on before. Okay, so typically we all do carrier sense, right? Carrier sense, first listen if something's going on the channel, and then talk. Now, for a system where we want to guarantee low latency, is that actually a good idea to do carrier sense multiple access? The answer is no, you're all right. The question is why? Why is that not a good idea?
Because you were studying listening first.
Yeah, you could be wasting a little bit of time listening, right? But at least in human communication, it's not, depends on whom you're talking to, but it's not that inefficient. But what happens? What happens to the nature of this system when you put in Karasense multiple access? Right? I have right now a sensor reading, or I have right now I'm the control node that generated the activation command. This is now time critical information that needs to go over the channel.
Jitter, non-deterministic.
It's non-deterministic, right? I want to access the channel, and I depend now on what is going on around me, right? And those other guys, they not necessarily know that I have time critical data, right? So it's a random medium access control scheme. No? And that's pretty bad. No? That's especially when you get into the business of seal and ACL and all these 10 to the power of, I don't know, whatever reliabilities, right? So this is exactly where Karasense multiple access is really bad. No? Okay, so what do? We still have all these systems deployed out there. No? So this work is now looking at the question: if you put the plant with a sensor here, and you put it into an environment where it actually has connectivity to multiple edge nodes that will be around, and I'm throwing my sensor reading not only in a dedicated way only to one point of computation over a wireless link, but because what I'm sending out wirelessly is anyway a broadcast signal, right? I'm broadcasting that into many different directions. What would happen if I just put in multiple of these controllers, these points of computation? And then, this is great from the perspective of the wireless channel, right? Because we just talked about it. I'm harnessing here spatial diversity. As long as these compute nodes are not stacked together, like 5 centimeters by 5 centimeters to 5 centimeters, this communication channel here is statistically independent in its evolution from this one here, and from this one, and from this one. So you get a lot of diversity if you have a significant amount of these compute nodes around. Now, if you do that, the one bad thing, though, is now you throw your sensor reading to all these compute nodes. They all receive it, or a substantial subset receives it. They will all do the computation, and they will all kind of like terminate with their execution more or less in a synchronized manner. And now they will all, at the same point in time, try to access the communication channel. Right? And if they do that over Karasense multiple access, hell breaks loose, right? Because they're all going to be colliding. Let's assume the channel is free. They're all listening. They're all determining, oh, the channel is available. They're all going to start transmitting, and then I have a hugely interfering, colliding wireless communication channel. And then, right, because they don't get acknowledgements here from the receiving node, right? They will retry and retry and retry. They will always stumble into the same situation, right? So the key question that we're trying to address is, with a certain design, how do we address this collision problem here, right? So we address two things now. We address, on the one hand, the reliability of the wireless communication channel, and on the other hand, we want to get rid of this collision characteristic with a particular design that we're putting in, and by that tackling, so to say, the major stochastic effects on the wireless communication channel. That's what this work is all about. Okay, good. So let's go a little bit more into the details. So the scenario is, think about a mobile robot in a factory or some other plant that is going on that has a little bit of mobility, right? And where you can also think of a setup where you're constantly in reach of at least 2 or 3 of these edge nodes. That's kind of like the fundamental assumption that is driving this work. Okay, and then these, right, so all are kind of like doing their computations here, and they receive the sensor readings. So what we do is we put in a certain control system, and then we put in a particular timing characteristic. And we say, so we have a linear continuous time plant model. So it's a continuous time model. but we're now sampling that only periodically with a certain sampling time Ts. And this sampling time Ts is kind of like here given always by these phases. So there's, let's say, some time in between. This is not a system that is extremely fast-paced. And then we have this transmission of the sampling, we have the computation, and we have the retransmission. And now what we do is we introduce this broadcast phase at the beginning. Then there's a certain amount of time for computations. We kind of like assume to be just of fixed time length. We don't deal with any uncertainty, let's say that the communication could take a little bit longer or so. We just put, say, there's a certain amount of time for the first transmission, and whoever receives the packet receives it, and for whichever node this transmission time is not sufficient, then the corresponding data is just not received. So that guy is kind of like out for that computational round. Okay, then whoever receives the data starts the computation of the control command. Here we have the state feedback controller. And now we have a phase where we first do contention resolution, and then we have kind of like the transmission. Okay, and the underlying principle of this work for this contention resolution is the following. So when these nodes, when the plant is transmitting its sensor reading to the compute nodes, and whenever the device that you're carrying around in your pocket is actually receiving data, the first thing that happens before data is received is that the digital circuits in your wireless transceiver estimate the channel. This is important in order to calibrate your receive circuitry, right? To amplify the signal and so on and so forth, and essentially to decode the signal in a correct manner. So, and I'm kind of like, all of you also do that, right? So whenever you're in a context, when you're communicating, when you're speaking to someone, you implicitly also kind of like immediately get the notion of, is the acoustic channel right now in a good state or not, right? Or is that person standing further away or speaking very, very silently, right? So this is all kind of like still quite natural. Okay, good. So with this information, with this channel information that you receive in the uplink transmission, now we bring in a certain order when these nodes actually start, when the compute nodes start to be actually answering. And as we want to harness diversity, what we put in as a rule is that in this, we kind of like bring in multiple contention resolution slots, and they're reserved. And they're reserved in such a way that the guy with the best channel, he should be transmitting first, such that he knocks out through the carrier sense multiple access scheme all the other nodes. Okay, and this is done by introducing so-called ranges of the signal-to-noise ratio, so of the quality of the wireless communication channel. And so when the received signal in the uplink from the plant to the compute nodes, to the edge nodes, when me as an edge node, when I'm measuring that the SNR, the quality of this wireless communication, is in a very good range, then that entitles me to transmit first when I did my computations and I throw back the activation command. Okay, and now you see immediately, right, if the signal swings drastically, right, if there's a strong fading process going on, this will kind of like always spread out my nodes, right? It will always, it's like sport teams in school are put together, right? When two people start voting, or start picking their classmates for a soccer team, right? The people that are kind of like first taken, those are typically the best players. That's a little bit the intuition here. You want to give the first slot to that guy in that point in time who has the strongest wireless communication channel. And by introducing that, right, so we notice we're not changing anything in the basic circuitry of the wireless communication channel. We're not introducing any fancy MIMO scheme. We're not, we're not introducing any new coding scheme or anything that is certainly around. We can just do that with any regular Wi-Fi transceiver out there. We need to reprogram a little bit how the Wi-Fi transceiver reacts here at the end. We only need to delay that according to the wireless communication channel. Okay, and I can do that, and this is now super important to recognize. I can only do that because it's a loop. And that is something that is in literature right now completely underestimated. The key thing in edge computing is, in many cases, you always have an uplink transmission and a downlink transmission, and this is going on between the two same nodes. What counts in terms of the communication quality, though, is the entire round trip, the quality of the round trip, the combined effect of the first communication, the computation, and the second communication. This is going on between two nodes. So in a sense, you could say it's a multi-hop transmission. If you treat computation also as a certain type of delay element, maybe with a random delay, it's a multi-hop transmission. But from a physical point of view, this multi-hop transmission is happening over one wireless channel in one particular state, if it's fast. And this has profound consequences for performance evaluation and for engineering these systems. This is completely unrecognized for the moment. So if you happen to if you happen to be looking for a good PhD thesis topic, and what you're doing is right now, maybe you're not so much interested. I don't hope so. And you want to get into wireless communications. That's the nut to crack for the moment. That's super important. You had a question.
Just to make sure I understood you correctly. So it's a kind of message you send out, and with this message you tell, I only want one answer, and the one who has the best signal answers first, maybe only if he has had enough time to do the calculation, maybe he's a little slower. So not only the best receiving, but also the fastest and best receiving get a chance to answer. And all the others listen. If there was an answer, they are quiet. Exactly,
That's pretty much how it works. Okay, good. So what can happen in such a system? What now, in order to get all this done, right, what you need is at least one guy needs to receive the broadcast, the uplink transmission. The computation we just treat as a deterministic process here. We don't put in any uncertainty about the compute time. You can do that. But in this very first step, we kind of like leave that out. And now what in this contention resolution phase, what you really need is that there's one guy, what you need is that in these ranges that you define for the quality that entitle you to access the channel first or second or third, you need to make sure that the guy who accesses first is really the only one in that quality bracket. That's the key thing. If you have two in that quality bracket, even if it's a great signal, they will be colliding again. And then, of course, so that's the way it is. Okay, good. And the other thing that can happen is that if you define here a particular range and you have here a lower quality in the lowest class, what also can happen actually is that after all your contention resolution slots, no one has been picking up the channel yet, meaning everyone has a really catastrophically or a really, really bad channel. Okay, and for that case, what we then put in is that there's still always kind of like one dedicated node, which is going to answer with the activation command, kind of like as a fallback solution. So that's kind of like what we weave into the mathematics. Okay, then all this kind of like leads here to a certain success probability. This is fundamental statistics. There's no magic in here. What you essentially want is you want to then maximize this success probability under certain constraints. And it turns out that this is a nice optimization problem, and this optimization problem can actually be solved, for example, by coordinate descent. Is essentially a convex problem. And there are some nice mathematical properties in here. I'm not going too much here into the details. Okay, and then what you stumble into is essentially, when you solve all that, there's an interesting trade-off in here. And the trade-off relates to how many classes of these contention resolution slots. How many of these slots should you introduce? And the trade-off here is, on the one hand side, if R gets bigger, if you have more of these classes, then your likelihood for a collision in the individual class goes down, because you're kind of like, with a bigger R, you're introducing more of these ranges, and these ranges then also get smaller. On the other hand, when R gets bigger, the time that is there in order for the last guy to transmit, for the kind of like for the backstop, that time diminishes. So you're cutting into that time, because what you want to keep constant is this overall loop time, the overall loop responsiveness. This is what we keep constant. Okay, so there's that particular trade-off in there. Okay, good. And then if you put in some values here in the numerics, then what you find is basically this. So we now look at the success probability here on the y-axis, and we go over the so-called average S and R. So what we do is we kind of like consider a setup where, on average, these compute nodes that are around the plant, they're all getting closer and closer and closer, meaning your average received signal on the uplink and on the downlink is getting bigger and bigger and bigger. So you can also say the scenario stays the same, and we just put in more and more transmit power on both sides. That's the same effect. Okay, so we're kind of like, from an energetic point of view, we're in a better and better overall average scenario. We're looking into the success probability here. We're starting here off, if we only dedicate one fixed controller to this communication, we're starting off with a terrible reliability. So reliability of 30%. So that's really, really bad. So your LTE system with which you're communicating is typically somewhere around 90% in its basic setup. And when you're communicating on Wi-Fi, you're also typically somewhere much higher, so around 80%. Okay, and now if you put in this broadcast control with actually 2 compute nodes, actually this reliability gets better. The broadcast gets, if you have actually more nodes, if it goes up to 6, you kind of like have twice the reliability on your feedback loop. Okay, and that translates, of course, into a particular step response here in your plant, where you see here the state evolution in time. And for the fixed control, you have these wild swings. And when you bring in broadcast control, then these swings are all much, much, much smaller. Okay. Is there any observation here?
I didn't get the big, like the N slots you introduce. So they are less than you have probably controllers around, or
no. This is the amount of controllers that we introduce.
Yeah, but like the number of nodes you have is the same or less than N you introduce, or how many slots? Because you said like it's a trade-off. Okay, we can have.
It's a trade-off in the R.
Yeah.
Yeah, exactly. Yeah.
Because what is the difference to the time
we run here with R equaling 10.
Okay.
It's a fixed R.
And what is the benefit now compared to time division multiple access, so that we already have dedicated slots?
Yeah. Which system has time division multiple access? Huh?
GSM.
Yeah, exactly.
But you can also use that for Wi-Fi, or can't?
No,
No.
it's not implemented in Wi-Fi.
Okay.
You could use it.
Yeah.
You could, but then you need to reprogram Wi-Fi. You need to ask Intel to give you access to their firmware API.
No, but I mean, like, for example, the slots you introduce here, couldn't you then tread like in TDMA? So you say, okay,
yes,
slot
of
one is
course,
for that
of course,
component.
of course.
Yeah.
But on purpose, we ask you the question, if we just go with consumer off-the-shelf equipment,
Okay.
cheap, inefficient equipment, right? Just by introducing a little bit this delay in the contention phase, essentially, with a very simple setup. What is it that we can achieve in terms of reliability? Okay, good. Good. So that's a small glimpse. If you talk to the 5G guys, they and I also have these slides from the last 10 years of research. Of course, we can also, when we put ourselves onto kind of like the green field, and we say, okay, whatever happened in the past happened in the past. Let's re-engineer everything. Then we're in this discussion of 5G and URLLC, so these super high reliable, low latency communication systems. Then we're also engineering somewhere around here in terms of reliability. So then the question is always, is it now 1 minus 10 to the power minus 6, or is it 1 to minus 10 to the power minus 7? And this is, from a theoretical perspective, meanwhile, relatively well understood how to build such systems under certain circumstances. We also have prototypes that have been built over the last 5 to 10 years. My group was also building such a prototype at some point. And we can also experimentally show that we can build wireless communication systems which harness either this type of spatial diversity or also frequency diversity, which are much, much more reliable in their individual transmission. The key thing here is always that these systems are complete redesigns. And that means let's say from a business perspective, you either need to do the new chip, and that drags you into a particular direction, or your Intel, and you can reprogram your chips. But that's the discussion that is going on, and that's also there, and we're going to see such systems sooner or later, either in 5G or in other domains. Okay, good. I think I want to leave it here. It's 9:57. I was supposed to end now, right? Do we have the program?
Yes.
Yep.
Yeah. And I was told now is a coffee break. Is that right or is that wrong?
Yes.
Excellent. Okay, good. So see you soon at the coffee break or later tonight. Thanks.